Schultz group.
Sorry.
And today I'm going to talk to you a little bit about time and temperature resolved crystallography, which is some of the work that we've been doing in our group and wider collaborative space in the Haber Institute in the University of Hamburg. I myself work at the Universität Kliniken Hamburg-Eppendorf, which is or the UKE. Sorry. So I will proceed on to the general topic today, which is how we are uh, adapting, I should say, serial crystallography and time resolved serial crystallography, and doing it both with temperature and also in time to look at enzymatic studies. So I'll start by there we go. Start by introducing. I have no real need in some ways to introduce to this crowd, but the classical methods of understanding protein dynamics has not usually involved crystallography, partly because, as nicely illustrated here by James Holton, when we measure a single crystal rotation data set, we end up with an ensemble measurement. So we end up with all of these potential dynamics happening at once, or potentially just a subset, depending on, because we typically measure at very cold temperatures, and essentially a sort of a resting state system. And so we either don't have certain dynamics occurring in our crystal, or we don't have a defined set of which dynamics are relevant and sort of functionally relevant dynamics. And so in order to turn the crystallographic experiment into a time resolved crystal experiment, we therefore go about triggering the crystal in some way, probing the crystal with some form of perturbation, be that temperature or most often light. And then we, after a given time delay, we record a data set. And that permits us to build up a series of snapshots that gives us a series of trajectories or structural snapshots of the enzyme or protein functioning in time. And so this has been done for quite a while. Biocars has been at the forefront of much of this. And typically, we've been doing this on light-triggered systems because they're quite available. There's been some move into other sort of general perturbations. And what we really focus on is sort of ligand probing, or probing the system by adding a ligand or substrate to an enzyme system and watching catalysis. That's really, really our focus. And so obviously the big boon in this space has been the development of serial crystallography, which I'm sure many of you are pretty well versed in. Obviously our advantage here is that we're shooting thousands of crystals once, and then we're merging the reflections from all of these separate partial diffraction patterns. And that means that the exposure time for the data set actually becomes the exposure time of a crystal, as opposed to conventional rotation, where the exposure time is much longer because you have to rotate that crystal in the beam. And therefore, we can start thinking about time resolution for our exposing beam in whatever the pulse we can generate. The extreme example of this is the X-Vels, which have very, very short femtosecond pulses. But also, and especially for some of our enzymatic work, and I'll talk more about this in a moment, we can go down into the milliseconds. At fourth generation sources, we're looking at microseconds, and this sort of permits us to explore a whole range of biochemistry available to us that may interest us, especially in the enzyme space. It also means we have less radiation damage at a room temperature, so we are spreading the radiation over all of these crystals, and therefore we can minimize radiation damage, and it's quite good for irreversible systems, because once we've triggered a system, we kind of throw the crystal away, and so therefore really the sort of one of the way forward to capturing these dynamic motions is via serial data collection strategy. And the methods for doing serial collection, or the self-delivery methods, are many and varied. I'm sure many of you are aware of the different ways of putting these crystals in front of the beam. The ones that we really use and have developed and pushed forward are the fixed target methods, which we think really do hold specific advantages for sort of time-resolved crystallography over others. And as I was mentioning earlier, we have what we're really trying to do is shift ourselves out of being totally dependent upon sort of the photoresponsive systems, which are have been studied extensively within some very nice studies, and into looking at more enzymological systems by developing the ways in which we're doing our pump, of our system. And one of the things this allows us to do is work more at synchrotrons, because you don't have so much requirement on your on having a really short pulse like you would at a FEL if you're trying to look at picosecond changes, because enzymes are just slightly slower, but there's a lot of interesting biochemistry that's happening in this millisecond to minute regime. And therefore, we think this is quite an interesting space to focus on. That being said, higher flux is still valuable. This is a nice paper I thought I'd point out out of John Beale's group and PSI, which just looks at the implications across your your kinetic regime, dependent upon the width of the pulse width of your probing beam, the pulse time of your probing beam, right? So if you can utilize a fourth generation synchrotron and do a microsecond time, you're able to achieve a much more sort of coherent exposure relative to the total lifetime of your intermediate across a given time series. So this is it's still very useful for us to be able to go down into sort of microsecond exposures. And then one of the questions that must be asked is, how well do protein crystals survive? And the answer, as we know for a very long time, is quite well. You can get catalysis to happen in a crystal just fine, and the crystal can survive. And this is one of Arwen Pearson, who is our institute director's favorite examples, which is methylamine dehydrogenase, which changes a lovely green to a clear color when you add the substrate, and actually induces quite a large domain rotation, which surprisingly is taken up by the crystal, essentially. Switches space group. And this is a very useful review from the 1970s, also a favorite of Arwen's, which essentially looks at what it means kinetically to start to diffuse substrates into a crystal. And the real thing here is they're pointing out that you still have activity. It's typically slightly slower, not always, and you have to consider the size of your crystal. So even because we essentially want diffusion to be the smallest, to be minimized as much as possible, right? So if you want a uniform trigger, much like in the same way we want a uniform trigger across all the molecules in a protein crystal, that's still true in the diffusion case. And they actually calculate a critical depth, which assesses how big your crystal can be before you start to become diffusion limited. We've actually found that you can kind of do quite successful time-resolved experiments with slightly larger crystals than indicated here, but it gives you a sense that actually it's important to also remind ourselves that the time-resolved experiment in a enzyme catalysis is quite different to a photo-triggered experiment. You have to think quite carefully about the kinetics of what you're measuring in a way that is maybe a little easier if you have a very rapid photosystem response in a light-triggered system, and particularly about questions of diffusion. And so our workhorse for doing these, as I've said since the beginning, is mostly a chip-based system, and we're mostly working at synchrotrons. And so we have developed, and I know you had Robin Owen on the last talk, and this is partly developed alongside them, these silicon chips in which we can load a large number of crystals, although relatively quite efficient next to other sample delivery systems in crystallography, and we can shoot 20,000 wells per chip. And we're heavy users of the T-Rex beamline, which is a specialized beamline at Petra 3 for time-resolved crystallography. And so it's a very robust system for us, and we can really focus on. We really have minimal issues beamline wise. I know if any of you've been to a FEL, you'll know the experience of can take quite a long time to get everything just working. T-Rex is actually really quite aims for simplicity to minimize that kind of overhead. And we're very lucky in our beamline scientist, David von Stetten, who is hugely helpful in performing these experiments. And so the way that we initialize this, again, I think Robin will have mentioned this, the adaptation of this development was the ligand is essentially ejecting a very small droplet of ligand onto each individual crystal and each individual well. And we can essentially selectively pump every single well with a precise set of controls. And this is one of the great advantages of the fixed target system to doing this, is that you can go to a crystal, pump it, give it a small droplet, and then you can come back later. And this is actually one of the strategies that we employ for minimizing the time it takes to do a time-resolved experiment or on the chip serially, is we can reduce the wait time, because we can essentially probe, pump a series of these things, a series of crystals, and then we can return to the beginning after a set delay time to then probe them all. And so we can sort of essentially do them in batches, and we can reduce the wait time between wells. Obviously, it would take a very long time to do this if you were waiting in front of every single well for even half a millisecond. And our example case of sort of proof of concept of this working is this enzyme glucose isomerase, or xylose isomerase, it's also known, which does the isomerization of glucose to fructose. So it's quite a nice system for us because the substrate is glucose, which can be made quite highly concentrated, and this is a 50 millisecond time point, which shows nearly full occupancy of the glucose in the active site. And it is a nice ES complex that comes out after just only 50 milliseconds. So you can see that we're able to push if the system is amenable, we can really push the time resolution down to milliseconds. The other system I'll talk about today is the CTX-M14 system, which is mostly the work of one of my fellow postdocs, Andreas, and which essentially is a beta-lactamase. So this is responsible for the breakdown of beta-lactam, the beta-lactam rings, and a lot of these types of antibiotics. It's got a really high medical relevance, and there are lots of interesting open questions about how this chemical process is, how exactly the beta-lactamases facilitate this chemical process. It's also quite typically crystallized. Beta-lactamase is typically quite crystallized quite readily. The issue always with the beta-lactamases is they're quite fast. So the glucose isomerase, especially at room temperature, and I'll talk more about this, is quite slow. And we also have a more challenging, slightly more relevant case in the beta-lactamase. As I mentioned earlier, it's important to consider the kinetics of your experiment. And at the beginning of the project, I know Andreas looked at lots of different substrates that could potentially bind sort of efficiently for a time-resolved experiment, and discovered that the beta-lactamase, the antibiotic proposaline, actually binds quite nicely to the active site quite rapidly for beta-lactamase, and doesn't just tend to give you product, which is one of the difficult sides of working with these enzymes. This is an example of the product complex at ultra high resolution. This is another piece of work that I'm not going to talk extensively about. Maybe you can ask me in the questions later if you have more interest, about measuring structures at ultra high resolution, which is done at P14. Some of the work with the global phasing and GLEB there. So this is a very high resolution product complex state for this. And you can also see this in some of the time resolved serial SSX data. And you can see that at 3 seconds, we can also get a well-populated intermediate state and product state. So Andreas here has modeled the covalent intermediate, because this is a covalent catalysis reaction, in green, and the product state in pink, and can assign relative occupancies to those. And I'll talk a little bit more about that later. So this is our other very well-behaved system for doing these measurements. And just to sort of round off the introductions of the example protein systems, glucose isomerase, as I mentioned earlier, is responsible for this opening up of glucose. It then undergoes a isomerization in its linear form and then recyclizes to a fructose. It's extensively used in the food processing industry, so it's got sort of industrial relevance, and it's quite a nice model system. It's quite easy to make this protein, and the ligand is, as I say, it's a quite kinetically nice ligand. You can get it. It's quite cheap, and it's quite small, and it's very soluble, which is very useful. And you can do your time-resolved experiment, your standard drop-on-chip experiment, and you can wait about half a minute, 60 seconds, 120 seconds, and you can see that very slowly we're going from a nice bound cyclized version to a linearized version that we can start to model. We can try to minimize the mixed nature of your time-resolved experiment as much as possible experimentally, but it will be mixed, and you will have to model mixed states into your data to fully understand it. And then you can see here that sort of very slowly we're getting the reaction to occur. And the reason for this is that XI is thermophilic. Glucosylteranose is thermophilic. So the question is, can we do this at a higher temperature? And this was the motivation for the development of time and temperature crystallography. And this is essentially putting all of the llama setup and system that I've already talked about into a temperature control box. And so we have essentially developed a T-Rex. They've developed the system for basically creating a controlled chamber, which essentially has a very fine temperature and humidity control, because obviously if you change temperature, you will change humidity. And if your crystals are exposed to very low humidity, they will dry out and break. And so we have a Peltier element that's essentially controlling the temperature, and then a series of other adaptations. So we have a Mylar window with air being blown in between to facilitate the exit of the X-ray beams, which is sculpted, the X-ray of the diffraction, which is sculpted to the detector at T-Rex. And we also have sort of on-axis viewing, which can also minimize condensation, which is one of the problems when you raise the temperature at very high humidities, is the box has a habit of turning into a bit of a rainforest. So this therefore allows us to do the temperature side of this. And we, as I say, we have fairly good control over this temperature. It maintains humidity to within 1%, and the temperature is stable to about 0.5 degree. And we have several independent sensors, so we can monitor the temperature of the box at all times. It takes some time to equilibrate, not too long. You obviously have to wait for the humidity to adjust as you change the temperature, but this is a fairly standard thing to do. We typically start at low temperature and we go to high temperature. It's easier to work in that direction. And so one of the first things we did was to look at to take our two model system and do a temperature series with them from low to high temperature. So in this case, 10 to 50 and 20 to 50 degrees. And we could then also look at the B factor distribution because we've kind of tried to minimize or keep uniform, I should say, the errors within our measurement. It's dangerous in a way to interpret too much into B factors, but they should ideally follow a log normal distribution when modeled. And if you plot that log normal distribution as a function of temperature, you can see that the mesophilic CTX-M14 responds very differently to the thermophilic glucose isomerase. So you can start to see potential adaptations to temperature in response to temperature. We can then also extend this further, so we can look at this as a function of the protein, and unsurprisingly, if you sort of map these B factor changes back onto the protein, it's the external. You find great inflation in the B factors in the external part of the protein, and the core has less of a change to the increase in the temperature. This is not too unsurprising, but what we can then also do is use Helen Ginn's rope analysis. This tries to look at the structure, all the structure's torsion angles or ideal torsion angles, and then measure the deviation in the data of the torsion angles from what's expected. And we can compare all of our structures in sort of rope space, so sort of torsion angle space, and we can see that there's a clear axis along which it proceeds with temperature. You can see we sort of go from one of torsion angle deviations, and we can map those back onto a protein. And this allows us to see that certain parts of the protein are experiencing greater torsion angle deviation than others. So we can start to locate where some of the protein is where the protein is sort of adapting, right, or is inducing specific motions in response to temperature. So between the sort of the B factors and the torsion angles, we can start to look at certain places that may be of interest for mutation studies or potentially for further work, essentially. And then, of course, now we have this entire setup, we can look at a kind of a temperature series on a time point rather than just a series of time points. And so this is the glucose isomerase again, but now we're at 60 seconds, where we at 20 degrees in the data I showed you earlier, and here see a primarily closed cyclized glucose. As we raise the temperature, we see essentially it turning into a sort of linear into its more linear form, and we can model that as a function of occupancy, because again these will be mixed states, and so you need to model both, and you can see that the occupancy of the closed state drops while the occupancy of the linearized state greatly increases as a function of temperature. Also, I'm just going to slight detour to say I'm a particular fan of the 2FOF map representation at the top here. The reviewer 2 on this paper didn't like this at all, but I like it because I think it very nicely shows the change in the strength of some of your density, which I think is less clear when rendered as a mere mesh. So the question then is, surely I could attain my linearized state if I just waited a bit longer? And the answer, interestingly, is also kind of no, because we actually can compare 60 seconds and 180 seconds, and you find that at 20 degrees, we're still principally at both time points in a closed state with minimal sign of like an open state. When we go to 50, we get that predominantly open state, and we lose that sort of closed density. And so it really shows you that we're kind of pushing the enzyme system into it, changing the thermodynamic equilibrium that you're seeing at different times, and thereby generating conformations that you would not otherwise observe if you just did the whole thing at a sort of standard temperatures. We can then also look back at the CTX-M14 case, and I would also so we can also look at the binding of our proposaline, I should say, to CTX-M14 at 3 seconds over a series of temperatures. I'd make another point here, which is that the same reviewer that didn't like our 2FOFC maps also didn't much prefer dead maps. But actually, I think CTX-M14 represents why dead maps are a slight problem with enzyme systems, which is that if you have, as we do in the CTX-M case, a sulfate that sits in the active site until it's displaced by the proposaline, it produces really weird features in the dead maps. You can see this quite clearly in the 30 seconds, where you see a sort of negative feature on the end of the ligand. But what you can clearly see when we go from 20 to 30 degrees at 3 seconds is a much greater increased sort of occupancy and presence of the ligand. So we're able to increase the amount of the bound population just by raising the temperature at 3 seconds, right? And this is even more so when we go up to 37 degrees C. So we see a full presence of the proposaline ligand. And this also allows us to pick out some unique states that occur that we don't see otherwise. So one of the interesting conclusions of this data, and Andreas is still working diligently on the rest of the whole time and temperature series, and I'm not going to delve too deeply into the beta-lactamases and their chemistry today, but essentially we can see a repositioning of serine 70, which is where we'd usually see which is normally participates in the covalent intermediate, as a function of the formation of the product state. And we see a slightly different product state position to other cryotrapped structures. And so again, working at these physiologically relevant temperatures, we're able to show certain conformations and structural adaptations that we wouldn't otherwise see. And Andreas has a very nice multi-conformation analysis. So if some of you are wondering how we do or how he's fitted all of these different ligands in over at the same time, there's a very nice paper that's just come out on bioRxiv that goes into that in some really nice detail. What's next? Well, the next step is the next enzyme system that I'm principally working on is the aminoglycoside acetyltransferase enzyme. This is a another antibiotic modifying enzyme, so we're covalently adding an acetyl group to an aminoglycoside. These would normally bind the ribosome and inactivate the ribosome. They don't, and when they're acetylated, they're no longer able to do this. And what's particularly interesting about AAC is that it shows it changes the nature of its cooperativity as a function of temperature. So it puts in a place to look at systems with known kind of temperature sensitivity in their behaviors, if you like. And so AAC essentially, as I say, has a positive that goes to a negative cooperativity in the case of the acetyl-CoA, and in the case of the aminoglycoside, it has a similar shift in its cooperativity that also occurs. And this is thought to be related to its dimeric nature, which is not uncommon. We've seen this in other systems that dimers are heavily involved in the process of allosteric. Well, basically have to be by definition, but in this cooperative process. And it's thought that essentially very subtle changes at the dimer interface are what's again driving, which is again unsurprising, is driving this temperature change. And we can start to explore those changes as a function of temperature, which, as you can see here, goes from around about 280 to 320, so quite moderate temperatures. There's degrees Kelvin, I should say, rather than Celsius. So fairly like around the range that we can now measure in. And we started in this project by measuring, by getting the first ternary complex for the AAC. Normally, it's hard to get the previously the aminoglycoside substrate has never been resolved in any of the crystal structures. And we've now made microcrystals of this and are doing sort of temperature series on the different substrates to try and see how the substrates, because what you will notice about the cis-myosin substrate in panel D here is that essentially the substrates also sit over and interact above the dimer interface. So we think there's a very interesting interplay between substrate interaction, dimer interaction, and how these cooperativity changes, these temperature-sensitive cooperativity changes are occurring. So with that in mind, the main takeaways is that the temperature control box at T-Rex is a very robust and versatile system for doing time and temperature resolved serial crystallography. It really allows us to explore temperature sensitive enzymes and also, as is shown in the CTX-M14 case, systems that don't typically respond to temperature, but still we can see distinct features only available at these relevant temperatures. We can explore, as I say, structural adaptations to temperature on ligand binding, some of the work that's been done by some others in our group, and generally look at structural explanations for some of these thermodynamic properties that we see, or odd thermodynamic properties we see in proteins. And so the feature is for where we're going is, as I say, investigating more protein systems with maybe slightly greater relevance to human health, and then feeding back what we're learning in our structural studies into a sort of wider kinetic and thermodynamic framework to better understand these sort of subtle dynamics. And with that, I will acknowledge my group, all of whom contribute to a great group atmosphere we have in the Schultz group, particularly Andreas and Maria, who've put a lot of work into the time and temperature crystallography. Pedram, one of the co-group leaders also the other group leaders at Haber, who's a long-time collaborator and heavily involved in this work, and Fridtjof and his engineering team at the Max Planck, who really are our kind of go-to people for getting things built and designed. And with that, I will draw to a close and take questions.